Hello, let's start.
Yes.
Okay.
Yes.
Okay, just to comment on previous exercises, is there any question about the exercise about the ROC curve? I've sent you a partial solution like this. I don't know if do you all understand now the meaning of the ROC curve? Is there any question about that?
No.
No questions?
No.
So which one is the good curve, the blue one or the red dots? Anyone?
The question was which one was the best?
The good one, the true ROC curve, is the blue one? Is the red dots? If they are the red dots, what's the curve? Do I need to, I don't know, is this the curve? Or which one is the?
The blue one is the curve.
The blue one is the correct one?
Yes.
Yes.
Why?
Because if you take the last column, then those are the red dots. But then for the blue curve, we have the values that are in the first and in the second column.
This is the blue curve. This is the red dots. I mean, according to the problem, this was the correct formula. This is just an approximation. The important thing here is to realize that we are computing the error curve from error counts. Do you see that? You remember this problem, I suppose. In this problem, we have 6 positive examples and 9 negative examples. Do you remember that? Then the only possible errors are fractions of 9 and fractions of 6. Do you see that? I don't know if someone is saying something. So do you see that all possible rates are just normalized version of counts? and that these counts has to be values from 0 to 6 for the positives and from 0 to 9 for the negatives. Do you see that?
Then it's the number of the fraction, no? The
All,
down number of the fraction.
again?
No? TP, it's because TP is 1 6 2 6, no?
Mm-hmm.
Then okay, yes.
So what I mean is that all possible values of the ROC curve have to be quantized according to the number of positives and number of negatives. The x-axis is quantized because it's FP, it's negatives. And the y-axis, which is TP, is positives. That's why we have all these quantized values. You see? So the ROC curve has to be a curve that lives in this quantized space. Something like this. All possible ROC curves have to be like that. Unless you change the data set. Is that clear?
Yes.
Okay. My question is, so in this particular case, how should I draw? Now you know that the red dots belong to the true curve. It's okay? It's okay?
Yes.
So what happens between this dot and this dot? How should I join these 2 points? Because I have several options. Could be like this, or it could be like this, or it could be like this. You see? The true.
Rect? It's a rect line between them?
You mean that?
Yes.
But then the curve is not quantized. You cannot have half positive correct and half positive incorrect.
Oh, okay, okay.
You understand what I'm saying?
Yes, 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 yes.
The curve has to be something like this, for example. But can I know the exact ROC curve with the information I have here? What exactly happens between these 2 red points? By the way, these 2. What has happened between these 2 red points? I have moved the threshold from -1, sorry, from 0 to 1. And then I have one more true positive. That's why I move up. You see that? And what has happened here? What has happened here? No one?
FP increment 3 point.
Okay, I have 3 false positives more. That's why I move 3 positions to the right. But what happens in between? This is theta equal to 0. This is theta equal to 1. When theta is 0, I have 3 true positives, 1 false positives. When I get to theta equal 1, I have 1 more true positive, but 3 more false negatives. All of them are in this region. The positive and the 3 negatives. Depending on the values which I compare this threshold, these positives and negatives between these 2 values of the threshold, then the curve will be this or this or this. I have no information to plot the curve with this table. You see that?
Yes.
Yes.
So it's with this information, it's impossible to know. I would need to fill the values for all different, especially negatives, because the positives are like 1, 2, 3, 4, 5, 6. So I have all possible values of the positives, but not on the negatives. Let me show you an extension of this information. For example, imagine you have something like this. Now we are looking at the output score. So we have a mapping. This is the input. We have a continuous output, and then we apply a threshold. The threshold is the value of theta. It's okay?
Yes.
Okay. If the output score is below the threshold, I decide positive. Why? Because I prefer putting the positives on the left. It's okay? And if the output value is above the threshold, I say negative. Imagine this information was not in the statement, but just imagine that the outputs for all possible positives and negatives are the ones shown here. We have 1, 2, 3, 4, 5, 6 positives and 9 negatives. But now, for example, we see that for values between -1 and 0, we see that the negative is on the left of the positive. For values between 0 and 1, the positive is on the left of the negatives. With this information, now we can plot the whole curve. The curve is plotted by looking at all possible position of the thresholds. When the threshold starts at -3, then I have nothing, 0, 0. because I have no positives on the left and no negatives on the left. You see that? Positives on the left, negatives on the left. It's okay? Then, when I move the threshold to 2, I have one positive on the left and no negatives on the left. It's okay? The same for theta equal to 1. And now I see that when in this position, I obtain, so it happens first that I have this false positive, this false positive, and then this true positive, this true positive. You see? So this means that from these two, between these two red points, the curve goes like this. You see? Questions? If I want to plot the whole curve, I need to put the threshold in all these different places. Is that clear?
Could you please repeat again how you decide with the threshold?
Well, the thing is, when I move the threshold from the left to the right, positive and negative examples are going to the left side of the threshold. You see?
Yes.
When I find a positive, then the true positive rate, gets increased when I find a positive. When I get negatives, then the false positive increases. So to plot the whole curve, I need to put the threshold exactly at the places that I have drawn here. Well, in fact, I should also put here and here and here. But when I have a whole block of negatives or positives, then the curve either moves vertically or horizontally. You see? Okay. I don't know how to better explain. Just to summarize, with the original information you had in this table, in the statement, you cannot plot the whole curve. You can only plot the red dots or an approximation. For example, the blue one, or for example, I don't know, whatever you like. Something like this is just an approximation. You cannot plot the real curve. To plot the real curve, you need to know all possible values that get compared to the threshold. With all this information, then you can plot the whole curve. For this particular example and this particular output values, for example, the whole curve would be that one. This is the exact curve if the outputs are the ones shown here. It's okay? And in all cases, the ROC curve is a quantized curve because it depends on counts of true positives and false positives. It's okay? Okay, you just think about it. No questions? Is someone
I have a question.
recording? Okay, yes. It's okay?
I have a question.
A question.
So you plot only the positives?
Excuse me?
You only plot the positives?
What do you mean? Oh, just the positives.
Or so that graph only
The
represents?
The curve.
Yes.
I'm plotting true positives against false positives.
The false values are, we don't care about false.
I don't understand you. I mean, true positives are positives and false positives are negatives.
Okay.
I don't know if you... This is a count on the 6 positives in my data set. And this is a count on the 9 negatives I have. I have 6 positives and 9 negatives. When I count true positives are among the 6 positives I have, and false positives are among the 9 negatives I have. I don't know if this is your question.
Yes, now I see it better.
You should. More questions? If you had several data sets and you do, for example, an average, or you could, for example, estimate probabilities instead of counts, then the ROC curve could be a smooth curve. But usually, we plot ROC curves using counts. So the curve is a quantized curve. It's okay?
Yes.
Okay. Any questions about the exercise on the Bayes rule? Any questions? Do you all understand the underlying concepts? How we obtain the weighted class conditional probabilities, just multiplying by the priors, then how to obtain the unconditional probability, just summing the weighted class conditional probabilities, and then how to obtain the posterior probabilities, which are the functions that we compare to decide. But observe that to implement the classifier, we can use either this or this, because doesn't matter. I mean, the boundary, which is here, where the two curves are equal, is the same as here. So, okay? But anyway, one thing is the weighted class conditional probabilities, and other concept is the posterior probability. It's okay? No questions?
No.
No questions. Okay. So let's go ahead. Now we are going to show how these boundaries and posteriors and conditionals looks like when the classes are normally distributed. Using Gaussian distributions for measurements, it's one of the easiest options and most well-known options, because in many practical cases, our measurements can be seen as distortions around typical values. These typical values are represented by the mean value, and then usually the measurements distribute around this mean value. Okay, this is what we already know as a Gaussian distribution. What you have in this slide is the exact expression for the Gaussian distribution for one dimension and for several dimensions, what we call univariate Gaussian and multivariate Gaussian. I suppose you are very familiar. I suppose you are very familiar with this expression, is the well-known Gaussian. I don't know if you are also familiar with the multivariate Gaussian. What is interesting in this expression is the use of this matrix. This matrix here is the inverse of the matrix. This matrix here is the covariance matrix for class I. This covariance matrix in 2 dimensions, for example, is something like this. This is the, well, in 1 dimension here, the parameters of the Gaussian is the mean, which is this value here. This is x. This is the mean. It's okay? And the other parameter is the variance. The variance is related to this. This value here, it's the variance. So the higher the variance, the wider the distribution. Okay? I suppose you all are familiar with this in 1 dimension at least. It's okay?
Yes.
In 2 dimensions, what you have is the variance the variance on the X, the variance on the Y. Imagine that you have X and Y. Variance on the X, variance on the Y, and then covariance of the X and Y. So this is a symmetric matrix. We only have 3 parameters: variance X, variance Y, and covariance. When we put this matrix inverted here, what we have here, observe that this can be seen as a distance from the mean. In 2 dimensions, if this is X, Y, and we have our mean here, then we have a variance associated to the X, a variance associated to the Y, and then how X and Y relate. If we have zeros here, then there are no relation between variation in X and Y, and we have Gaussians like this or like this in 2 dimensions. If we have here values different than 0, then we have Gaussians like this or like this, because values of X and Y are related, in fact, are correlated. This expression here is what we call the Mahalanobis distance between X and mu. Observe that if the covariance matrix was this, in this particular case, this expression becomes the Euclidean distance. Because X minus mu transposed multiplied by X minus mu is equal to X minus mu like this, for this particular case. So what we have here is a modification of the Euclidean distance according to how this Gaussian is, how values of X and Y are related to each other. Graphically, we can see here an example of a two-variate Gaussian distribution for a particular covariance matrix, and we are shown here, these lines here are places that are at the same distance from this. This is the mu. So all points in this curve here are at the same Mahalanobis distance from the mean. It's okay? Questions? Questions?
No.
Okay. Okay. For this particular form of the distributions of each class, we can obtain exact values, exact expressions for the Bayes classifier. So that's what we are going to do now. Observe that these functions, this is the most general case, is an exponential function. So all the probabilities, conditional probabilities, etc., are going to be like this. So if we take logarithms, here, no matter which logarithms, if we take logarithms of that, then what we obtain are expressions that are proportional to this Mahalanobis distance. You see? So at the end, the decisions and the Bayes rule and correspondingly the boundaries will be defined by this, which is nothing but the Mahalanobis distance, which is an variation and extension of the Euclidean distance. So at the end, we are going to compute distances to obtain the boundaries, because the particular form of these distributions are exponential functions applied to a kind of distance, square distance to be exact. Okay? Okay, let's start. Let's assume only two classes. And if you remember the expression of the Bayes rule, you remember the expression of the Bayes rule? You remember it was prior, conditional, unconditional. You remember that?
Yes.
But when we define the discriminant function, we can just take this out because does not depend on I. And when you take logarithms, instead of a product, you have a sum. Sum of the logarithm of the conditional and logarithm of the prior. It's okay? Okay? So this is the expression, one expression of the discriminant functions corresponding to Gaussian distributions. Developing this, we have this general equation. It's okay? What kind of function we have here in terms of x? Well, we have x here, just parameters here. This is a quadratic function because all this is a constant. You see? So if I want to compute the Gaussian classifier, the Bayes classifier for the Gaussian case, I need to compute quadratic function, in particular, hyperquadrics. That's why something like this, for example. Hmm? Because this is only c is equal to 2, we can compute just one discriminant function and then decide depending on whether this is greater or smaller than 0. This function is just the one we've seen, that one. And this equation is the one that gives us the boundary. So the boundary is also a quadratic function. In this particular case, this parabola here. Okay? In other words, this is sorry. This is the mean of class 1, for example. This is the mean of class 2. This is the Mahalanobis distance from the mean of class 1. This is the Mahalanobis distance. Oops. No. Shit. This is the Mahalanobis distance corresponding to class 2. And for example, this point here is at the same distance from one class than from the other class. That's why this point belongs to the boundary. It's okay? Questions? Questions? No questions?
No.
Perfect. I don't know what's happening here. Something has happened. Sorry, don't know what's happening. Okay, here again. So no questions? Okay, so let's see what happens when coverage matrix are like this, which means for example, in 2D, this would be 1, 0, 0, 1 multiplied by a constant. This constant would be equivalent to the variance both for X and Y. It's okay? In this particular case, the previous expression simplifies because this just disappears, and this is a constant that can be neglected. So at the end, we have this expression here, which is just the distance, Euclidean distance, and then the logarithm of the prior. It's okay? If we develop this, then we obtain here is the quadratic part of this expression is here. This is the mixed linear part and the part depending on the means. But what happens here is that this quadratic part does not depend on the class. So I can change this discriminant function. I can just take this out because does not depend on I. And then we get a discriminant function like this. What's the big difference between this and this? Without that, the big difference is that this is quadratic and this is linear. You see? It's okay? Okay. So, for example, here, if we have a Gaussian like this with mean here, and a Gaussian like this with mean here, the boundary between these two is just a linear boundary because it is obtained equating a linear function to 0. It's okay? So the Gaussian Bayes classifier, if the covariance matrices are diagonal, well, diagonal with the same value here, reduced to a linear classifier. It's okay? There are other particular cases. For example, let's consider the case in which we have a general coverage matrix, but does not depend on the class. You see? So we can have covariances like this, but they have to be equal for all classes. Class 1, class 2, class 3. General coverage matrix, but the same for all classes. It's okay? In this particular case, we can observe that when we compute this, then what happens is that the quadratic part of the expression is here, but this part does not depend on x. The part that depends on x is here, and we have also a linear function. Okay? So this could be perhaps surprising, but it is not. I mean, it happens that, for example, here, covering like this, covering like this, but when you consider Mahalanobis distances here, like this, for both classes, then the places which are at the same distance from both means belong to a line. It's okay? Okay. You may perhaps remember that when we were having a look at some expressions, we were having a look at, without going into details, but we already had a look at the code corresponding to the scikit-learn toolbox. And we were looking at the outputs of a particular mapping, particular classifier. This classifier was called linear discriminant analysis. So this linear discriminant analysis you have here is exactly this or this. So this is how this toolbox computes the linear discriminant analysis. So it assumes that the classes are Gaussians. It assumes that the covariance matrix has to be restricted to any of these two cases, and then obtains the corresponding linear discriminant function. And the output of this linear discriminant function is exactly what you have here. The outputs, in this case, we had three classes. So we have three discriminant functions, and these are the output, not that one. If you remember what we did the other day, this decision function here, this, what you have here, are the outputs of the discriminant functions. Exactly this or this. It's okay? You will be having a session, lab session, in which we will have a look at these classifiers. It's okay? If you want to have a look prior to this lab exercise, you can have a look at the following information. Let me okay. If you type scikit and then You already have here the information about scikit-learn.org. You have here all the information about the toolbox we are going to use in labs. We will introduce this thoroughly, but it's just now a quick look. If you type here, for example, linear discriminant, then you have here scalar discriminant analysis, linear discriminant analysis. For example. And now you can go to the module corresponding to discriminant analysis. And you have here linear discriminant analysis, which is these two cases, and quadratic discriminant analysis. This quadratic discriminant analysis is nothing but this. Okay? So what the toolbox does when you use this quadratic discriminant analysis, instead, for example, of linear discriminant analysis, then it assumes that the classes are Gaussian and that the covariance matrix can be of any form. Then what you obtain is a quadratic function. And then what you have in this case as output of the decision function method is the output of the different quadratic functions associated to each class. Okay? So this is the theory behind the linear discriminant analysis and quadratic discriminant analysis. Questions? No questions?
No.
So I had another view of the same thing. Let me show you this. Okay, what you have here is an example of a Gaussian data set. These are examples that have been generated randomly from a Gaussian distribution in one dimension. These are the values. Values have only one dimension, which is that one here. These values are normally distributed around 0. And the variance is, let me have a look. The variance is 1. These examples have been generated with 0 mean, variance 1. If we compute the histogram of this set, we obtain that one, which is, well, I don't know if it's very, very Gaussian, but I mean, if we have here 100 examples, let's repeat the same with, I don't know, 10,000 and see what happens. Now we see basically nothing here, and the histogram is resembles more a Gaussian. You see? In fact, if you plot the same histogram with perhaps more bins, let me try. Is the same histogram, but with more bins. And this is basically very, very close to a true Gaussian. You see? Okay. What happens if we generate data in 2 dimensions? Let's see what happens.
Como he visto la luz que está a tiempo sin verte,
Sí,
quiero saludarte, ya está.
si estás de juego, no vemos.
Ok, venga.
Okay. What about the break? Hello.
Okay.
Okay. Let's do a small break.
Okay, okay.
And please ask something or say something because I'm quite alone here. Okay, 5 minutes break. Hello?
Hi.
Okay. Questions? No questions. Okay, what you see now is just another random sample of 100 points distributed normally around 0. And as you can see, the histogram is, well, quite bad. But I mean, it's just a random sample, okay? Okay, let's see what happens in the two-dimensional case. Okay, this is a random sample of size 100 of a two-dimensional Gaussian. If you are curious, this is the covariance matrix of this example is, well, is the identity matrix. So this is the samples are distributed normally around 0. 0 is here, 0, 0, and the covariance matrix is the same for X and for Y. Okay, let's see what happens with a non-diagonal covariance matrix. Now, as you can see, let me just okay, much better. Okay, now you are looking at the appropriate Gaussian. The coverage matrix is, let me, in this example, the coverage matrix is that one. Let me show you. 1, 3, 0.8, 0.8. This is the coverage matrix corresponding to this. So the covariance in the X is 1, in the Y is 3, and the covariance is 0.8, which means that X and Y are positively correlated. Then we have this shape of the Gaussian. Okay? Okay, we can also generate data corresponding to two Gaussians, like this. Oops, what happens? Like this. Okay. Let's show things properly. Okay, much better. So now we have one of the classes, the red one. Okay, none of them are uncorrelated. One of these has positive correlation and the other one has negative correlation. But anyway, there are just two Gaussians. We can show, for this particular example, we can show the Bayes classifier. I mean, the boundaries of the Gaussian classifier corresponding to this example. Because as we know, the exact covariances and means which we have used to generate the data, then we can compute exactly the Bayes classifier, which is that one. I mean, well, this looks like quantized, but this is because I don't remember. Can't remember. It's okay. This function is something like, if we could plot this smoothly, this is an hyperbola like this. I mean, well, no. For example, so it's a quadratic function like this, but it's rotated and adapted to the data. You see? Here. The important part of this function, obviously, is this part, because it's the part that separates the two blobs of the data. So what means this part of the boundary? What does this mean? Well, what it means is that if I had an example in this region, the probability of belonging to the red class is higher than the blue class. You see that? Examples in this region correspond to places where the posterior probability of the red class is higher. Red class here, blue class here, blue class here. Okay? Okay? We can plot. Okay. We can plot the lines corresponding to the values of the Mahalanobis distance to each of the two means. To try to understand what is happening here. So the black lines correspond to places that are at the same Mahalanobis distance of the two different means. And also, we can plot okay. Something has happened here. Oh, sorry. I need to plot all of it again. Okay, let's start again. To be able to see this, we need to this. Oops. Just a minute. No. Okay. It was a matter of aspect. Sorry. Okay, now we see the feature 1, the feature 2, the x and the y's, and on the z, we have the value of the corresponding distribution functions for both classes as surfaces. Now you can see how they look like. So the boundary is more or less around this place, and then it rounds like this. Okay? But obviously, the data are only at these regions. Okay? While the boundaries extend, obviously, to the infinity. It's okay?
Yes.
Yes.
Questions? We can show some more examples corresponding to, oops. I get an error, sorry. Okay. This is an example in which we have generated data from two classes, and we have, well, we have very, very few data. So the true exact Bayes classifier is this black line here, which is a quadratic function. You see? And what if we take this data and estimate the mean and the covariances from data? Well, if we do that, then we obtain approximations on this true boundary. For example, this is the quadratic approximation when we compute parameters from the data, and this is the linear approximation when we compute the parameters from the data. So you can see the big difference we obtain. It's okay? Okay, this was not the example I wanted to show. The example I wanted to show is that one. Okay. Okay, now this is the same examples you had in the slides, but now you can look at them interactively. You don't have this code because this code runs in MATLAB, so we are not using MATLAB in principle anymore. So, and for these examples, you have the data, the case of hyperspheric Gaussians. You can see the class conditional probabilities of the two sets of data. And then you can also see the posterior probability. This is the posterior probability for class 1. Class 1 is the blue one. So this function, it's a value between 0 and 1, because this is a probability. And this is a density. That's why the z goes from 0 to 0.08. Posterior, because the decision boundary is linear, the posterior has this shape like a step, smooth step, as you can see. It's okay? Posterior, conditionals, data. For the hyperspheric case, we also have what happens if the Gaussians are hyperspheric, but the variances are different for the both classes. Okay, you can go now to the slides and try to figure out what's happening. But I tell you, the boundary is quadratic. How it looks like? Well, because one of the Gaussians is wider than the other, it also means that one is taller than the other. And correspondingly, the boundary gets curved around the narrow one, like this. What's the shape of the posterior? Well, this is the shape of the posterior. The step we had previously gets rounded, gets curved around the narrowest distribution, more or less like this. It's okay? Questions? More cases. What happens if the previous example, we make even bigger the difference between the two variances? Well, the boundary gets more curved to the point that it closes here. So now the difference in height is much bigger, as you can see, much bigger, and the boundary gets more curved. And at the end, it becomes almost a circle around the first Gaussian distribution. It's okay? Questions? More cases. What happens if we have two Gaussians, hyperspheric ones, different variances, but the same mean? Both Gaussians are centered at 0. What happens? Well, we cannot see anything here because we have one Gaussian on top of another, but one of them is wider. So the posterior looks like this. Okay? which means that the boundary is a circle. I don't know if this is clear. This situation in one dimension would be something like this. In one dimension, we have a wide Gaussian centered at 0 and a narrow Gaussian also centered at 0. Which is the optimal boundary? Well, the optimal boundary is here and here. So inside in this region, the highest probability corresponds to the narrow one, and outside, the highest probability corresponds to the wider one. The same in 2 dimensions is this circle. It's okay? Questions? No questions? Are you awake?
Yeah.
Okay.
Yes.
No questions?
No.
Okay. What happens if you have general Gaussians, but the same for the 2 classes? Well, as we said, well, they are hyperellipsoidal. They don't look like this because the scale here has been changed. They are hyperspherical. And then what we have is a posterior like this. And the boundary is linear. The boundary is always linear if the coherence metric is the same for all classes. In the case of hyperellipsoidal and in general, but this is the case of hyperellipsoidal. For example, now we have arbitrary Gaussians, but the same for the 2 classes. Now, as you can see, they are not hyperellipsoidal, but the boundary is linear. As you can see. This is a case similar to the one we've seen in the slides, but here all the 2 Gaussians, the blue one and the red one, are uncorrelated. So in the blue one, the Y variance is higher than the X variance, but covariance is 0. And also in the red case, but contrary to the blue one, the X variance is higher and the Y variance is smaller. And moreover, the means are located at these positions. With this situation, the boundary is this quadratic function. If you want to have a look, this is how the conditional produce looks like. And this is how the posterior looks like. As you can see, posterior, here is the zone corresponding to the red points. Here is the point corresponding to the blue points. But then there is a region that will become, if you move in this direction, you will find a region like this without points. But probabilities are the same here and here, and the same for this region. You have blue points here, but in this region, you have the same probabilities without blue points. It's okay? That's because the shape of the discriminant functions. This is a case with two arbitrary Gaussians. And this is the corresponding decision functions. We can have a look at the conditionals and the posteriors. Now this region is slightly more apparent here. It's okay? And what do we have here? Well, this example is similar to the previous one, but now the Gaussians are exactly aligned with regard to the position of 0. This is the position 0, 0. The first mean is, I don't know. Yeah, it's 0, 8. This position corresponds to 8. And this position corresponds also to 8. So this is 0, 8, and this is 8, 0. In this particular case, the boundary is linear. Well, this is not exactly linear. This is the hyperbola, but at the limit. I don't know if you see what I'm saying. In practice, the boundary between these two classes is a linear function. The same happens if you have these two Gaussians like this. The boundary is exactly the same as before. If you are curious, this is how the conditionals look like. And this is how the posteriors look like. And I don't know what's that. Well, now if we slightly change these Gaussians, it becomes apparent that what we have in fact is not a linear function, but an hyperbola, but at the limit. This example and the previous one are very, very, very similar, just slightly modified. Conditionals and posteriors. It's okay? Questions? No questions?
No.
Okay. So if everything is clear, I hope it is, this particular kind of classifiers are of theoretical interest, but also in practice they are still used for easy problems. In all toolboxes, the linear classifier and the quadratic classifier are implemented. And you can still use them, but you have to be aware what they mean exactly. The problem is that you are assuming the data is Gaussian, and the data is only Gaussian for very, very easy problems, not for the real challenging problems. And but it's interesting to see that the methodology is going to be the same. At the end, we have set up a particular shape of our discriminant functions, either linear or quadratic, and they depend on parameters, in these particular cases, mean and covariances. How can we compute then the discriminant functions? By estimating the parameters. If we have data, what we need to do is to estimate the parameters, namely means and covariances. If we assume that the covariances are diagonal, or even we could assume that the covariances are the identity matrix, we can assume that. Then the only thing we need to do is to compute the Euclidean distance. Euclidean distance to the mean. If not, then we have to compute the Mahalanobis distance. It's the same, it's equivalent. To estimate parameters, in general, we have a set of examples. In the case of the Gaussian classifier, we need to separate the examples by classes, and then we estimate the parameters for each class. So imagine that this is imagine that this corresponds to examples from one of the classes. We assume that these examples have been obtained from a particular distribution, Gaussian distribution. What we need to obtain is what we call the parameter vector, that in the Gaussian case, this parameter vector is the mean and the covariance. Okay? And the question is, how likely is that a particular set of examples has been obtained from a Gaussian distribution with parameters theta? We can measure this likelihood, this probability, with what we call precisely the likelihood of the parameter theta with regard to data set D. If we assume these examples are independently and identically distributed, then the probability of each of them has been obtained from this distribution can be obtained by multiplying all these quantities for each one of the examples. Now imagine that this P is the Gaussian function, E up to the whatever, x minus mu, blah, 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 blah. You have this expression. You can plug this example here. You can plug the parameters to the mu and to the covariance, and you can compute this amount. I mean, you have your Gaussian here, you have your example, whatever example it is, and you can compute this value, and then you can compute this product, and then you obtain a likelihood. At the end, we want to obtain what is the value of the parameters that maximize this likelihood. This computation can be done in some practical cases, and Gaussian case is one of the cases you can make this computation. You need to maximize this likelihood, or equivalently, the logarithm of it. Well, the logarithm of all of this, but the logarithm of this is the sum of the logarithms. It's okay? And this is what we usually do. If this is Gaussian, then we get rid of the exponentials thanks to the logarithms. And then the problem becomes quite easy to solve. To maximize, we just need to differentiate and equating to 0. And if we do this, well, let's skip the details. But at the end, we can obtain, well, this is for the dimensional case, which is easier. And we obtain that the mean has to be estimated like this, which is the usual way to compute the mean. And the variance has to be estimated like this, which is the usual way in which we estimate variances. Okay? And we can generalize that for any dimensions, and we obtain these expressions. In this expression, take into account that these are vectors. These are vectors, and that this is a matrix. So here we have a vector by vector, which is a matrix. And this is a sum of matrices. This way of estimating the coverage matrix is called the maximum likelihood estimate of the coverage matrix from the data. It's okay? Which are the usual way. This is not the only way in which we can estimate parameters, but this is the easiest one. Okay? Okay, and this is what we usually do with some minor details when we implement the linear and the quadratic classifiers. We estimate means and covariances basically this way. Other options to finish is, for example, what we call the naive Bayes classifier. When we say naive, it means that we assume that there are no dependencies among features, among dimensions. Well, if we assume that, it means that we can solve the problem. For example, if we have, let's assume we have 3 dimensions, 1, 2, and 3. If this is true, we can solve the problem in one dimension, in the other dimension, and in the other dimension. At each dimension, we estimate a probability. And once we have these 3 probabilities, we just multiply them because they are independent. And then the problem is very easy to solve because you are combining classifiers in one dimension. Everything is much easier in one dimension. Moreover, in one dimension, we can assume that in one dimension, for example, the data is not Gaussian or not even unimodal. And then it's relatively easy or easier to separate data with just one dimension. I mean, there is a full set of methods that are called naive Bayes. Because naive Bayes means that you solve the problem in one dimension. But how? Well, If you use Gaussian, then you have Gaussian naive Bayes. If you use linear functions, whatever, then you have another family of naive Bayes classifier, and so on. Okay? There is another family of methods called semi-parametric methods, because when we say parametric, it means that we are looking for particular distribution at the corresponding parameters. Variance, mean, or whatever. What we call semi-parametric methods is a family of methods in which we can approximate other distributions. Imagine you have a distribution like this. This is obviously not Gaussian, but we can approximate that as a mixture of 1, 2, and 3 Gaussians. You see? So you could consider this kind of mixtures to approximate other, perhaps more complex distributions. This is a family of methods. We are not going to study them, but okay. It's okay? Questions? No questions? I will probably upload an exercise related to all that. I don't know if you have questions with all the concepts we've seen. You can ask them through the tutorial system. If not, well, the next class would be about distances, classification methods based exclusively on distances, because that ones are related to the distances. This Euclidean distance, Mahalanobis distance, but just indirectly. We can also develop methods that directly use distances instead of distributions. It's okay?
Yes. Yes.
So if you have no questions, no?
No.
So bye-bye.
Bye.
Bye.